We are going to watch something unfold that arrives quietly, not through declaration, but through measurement. And if you can, set this to full screen and consider subscribing, because what follows is not brief, and then we can begin. The James Webb Space Telescope looked deeper than ever, and what it found does something more serious than add detail. It forces a rewriting of the map. Not the map as a drawing, but the map as a framework, the structure we use to think about when things happened, how fast they happened, and what the universe was capable of doing in its earliest moments. To understand what it means to look deeper than ever, we need to return to the most basic principle of observational astronomy, which is that looking farther away is looking backward in time, because light moves at a finite speed and the distances are so vast that the travel time becomes a substantial fraction of the age of the universe itself. When we say Webb looked deeper, we mean it collected photons that have been traveling for longer than nearly anything we have collected before, photons that left their sources when the universe was a smaller fraction of its current age, and this is not a metaphor. It is a direct physical consequence of the speed of light being fixed at approximately 299,792 kilometers per second in a vacuum, and the universe being approximately 13.8 billion years old. If you see light from an object that has been traveling for 13 billion years, you are seeing that object as it was 13 billion years ago, when the universe was only about 800 million years old, roughly 6% of its current age, and this is the regime Webb was designed to probe with unprecedented clarity. But depth is not just about time. It is also about sensitivity, resolution, and the wavelength of light being observed. Webb's instruments operate primarily in the infrared, from about 0.6 microns at the short end, which is barely into the near-infrared just beyond what human eyes can see, all the way out to 28 microns in the mid-infrared, which is deep into the thermal regime where warm objects glow not from reflected starlight, but from their own heat. This range was chosen deliberately because of a phenomenon called cosmological redshift, which stretches the wavelength of light as it travels through an expanding universe. Light that was emitted as ultraviolet or visible light from very distant, very early galaxies arrives at Earth shifted into the infrared, and the farther the source, the more extreme the redshift, and therefore the longer the wavelength we must observe to catch that light. This is why infrared capability is not optional for probing the early universe. It is the only way to see objects at high redshift, because their light has been stretched beyond the range of optical telescopes. The depth achieved by Webb is also a function of its collecting area and exposure time. The primary mirror, composed of 18 hexagonal segments made of gold-coated beryllium, has a combined diameter of 6.5 meters, which gives it a collecting area of about 25 square meters, roughly 6 times larger than the Hubble Space Telescope's mirror. More collecting area means more photons captured per unit of time, and more photons means fainter objects can be detected. But sensitivity is not just about mirror size. It is also about how long you stare at a patch of sky. Webb's deep field observations, like the famous images of regions such as SMACS 0723 and the Hubble Ultra Deep Field revisited at longer wavelengths, involve exposure times that can stretch to tens of hours, sometimes accumulated over multiple visits, and during that time the telescope is essentially counting photons one by one from objects so distant and faint that their light contributes only a handful of detectable photons per hour to the detector. The longer you expose, the more signal accumulates, and crucially, the more the signal rises above the noise, which is the random variation inherent in any measurement system, coming from the detector itself, from thermal emission, from warm parts of the telescope, or the zodiacal dust in the solar system, from cosmic rays striking the detector, and from the fundamental quantum uncertainty in the arrival of photons. To minimize noise, particularly the thermal noise that dominates in the infrared, Webb operates at extremely cold temperatures. The sun shield, a 5-layer structure roughly the size of a tennis court, passively cools the telescope by blocking sunlight and radiating heat into space, allowing the mirror and instruments to reach temperatures around 40 Kelvin, which is about minus 233 degrees Celsius. The mid-infrared instrument, MIRI, requires even colder operation and is actively cooled by a cryocooler to about 7 Kelvin. At these temperatures, the telescope's own thermal emission is minimized, allowing it to detect faint infrared signals from distant objects without being overwhelmed by its own glow. This is a fundamental requirement. You cannot observe faint infrared sources if your telescope is warm, because a warm telescope is itself a bright infrared source, and the signal you are trying to detect would be lost in the glare of the instrument itself. Webb's location is also essential to its depth. It orbits the Sun at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth in the direction away from the Sun. At L2, the gravitational pull of the Sun and Earth balance in such a way that an object placed there will orbit the Sun at the same rate as Earth, remaining in a fixed geometric relationship. This location allows the sun shield to block the Sun, Earth, and Moon simultaneously, all three major sources of heat and light that would interfere with infrared observations. It also provides a stable thermal environment, because the telescope is not cycling in and out of Earth's shadow as it would in low Earth orbit, and this thermal stability is critical for calibration. If the temperature of the telescope varied over time, the noise characteristics would change, the optical alignment would drift, and the data quality would degrade. When we speak of a deep field observation, we mean an image of a very small patch of sky, often only a few arc-minutes across, which is a tiny fraction of the full sky. 1 arc-minute is 1/60th of a degree, and the full sky spans 41,253 square degrees. So a field a few arc-minutes on a side represents only a few millionths of the sky. Yet, within that tiny patch, if you stare long enough with a sensitive enough telescope, you can detect hundreds or even thousands of galaxies, most of them very distant, and from the statistical distribution of those galaxies, their brightnesses, colors, redshifts, and spatial clustering, you can infer properties of the universe as a whole. This is possible because the universe is, on large scales, statistically homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations once you average over sufficiently large volumes. Therefore, a small, carefully chosen patch can serve as a representative sample, and the deeper you observe, the farther back in time you reach, and the more you learn about the early phases of galaxy formation and cosmic evolution. The map that is being rewritten is not a literal spatial map, though spatial distribution matters, but rather a timeline, a sequence of events, a set of relationships between cosmic time and the properties of galaxies, how massive they were, how many stars they had formed, how quickly they were forming new stars, how enriched they were with heavy elements, how organized their structures were, and how common such objects were at different epochs. Before Webb, this map was constructed primarily from observations by Hubble, Spitzer, and ground-based telescopes, along with deep spectroscopic surveys. Those observations had reached back to redshifts of 7, 8, even 10 or 11 in a handful of cases, corresponding to times when the universe was 500 to 700 million years old. But the data at those highest redshifts was sparse, uncertain, and limited in wavelength coverage, because Hubble's sensitivity drops off in the near-infrared, and Spitzer, though a powerful infrared mission, had a relatively small mirror and coarser resolution. The map suggested that galaxies at those early times were small, faint, low in mass, and still in the early stages of assembling stars and structure, consistent with hierarchical models of galaxy formation in which small objects form first and merge over time to build larger systems. The expectation was that Webb would see more of these small, faint, early galaxies, detect them more reliably, measure their properties more precisely, and perhaps push the frontier slightly earlier, but the overall picture would remain qualitatively similar. What Webb found instead was that some of the galaxies at high redshift are brighter, more massive, more luminous, and in some cases more extended and structured than the models anticipated. This does not mean the models are entirely wrong, but it does mean they are being pressured, forced to adjust, and the adjustments are not trivial. They involve reconsidering the efficiency of star formation, the initial mass function of stars, the role of dust, the timing of chemical enrichment, the prevalence of compact starbursts, the contribution of active galactic nuclei, and possibly even the fundamental assumptions about how dark matter halos host and regulate the formation of galaxies in the first billion years. To grasp what this pressure really means, we must understand how the map is constructed from observations, starting with the most fundamental measurement: redshift. Redshift, denoted by the symbol Z, is defined as the fractional change in wavelength of light due to the expansion of the universe. If a photon is emitted at a wavelength lambda emit and observed at a wavelength lambda OBS, then Z equals lambda obs minus lambda emit divided by lambda emit. For example, if a photon emitted at 500 nanometers, which is green light, is observed at 1000 nanometers, which is near infrared, then Z equals 1. Redshift is directly related to the scale factor of the universe, which quantifies how much the universe has expanded between the time of emission and the time of observation. The relationship is that 1 plus Z equals the ratio of the scale factor at observation to the scale factor at emission. So if Z equals 1, the universe has expanded by a factor of 2 since the light was emitted. From redshift, one can calculate the cosmic time at which the light was emitted, and the distance to the source by integrating through the expansion history of the universe, which depends on the cosmological parameters, the Hubble constant, the matter density, the dark energy density, and the curvature. These parameters are now known with reasonable precision from observations of the cosmic microwave background, supernova surveys, baryon acoustic oscillations, and other methods. So, given a redshift, we can compute the corresponding age of the universe, the look-back time, and various distance measures. For example, a redshift of Z equals 10 corresponds to a time when the universe was roughly 470 million years old, about 3.4% of its current age, and a redshift of Z equals 14 corresponds to roughly 290 million years, about 2.1%. These are the regimes Webb is probing, but measuring redshift is not straightforward, and the uncertainty in redshift propagates into uncertainty in all derived quantities. There are two primary methods for measuring redshift: photometry and spectroscopy. Spectroscopy involves dispersing the light from an object into a spectrum, a plot of intensity versus wavelength, and identifying specific spectral features such as emission or absorption lines from hydrogen, oxygen, or other elements. These lines have known rest frame wavelengths from laboratory physics, so by measuring where they appear in the observed spectrum, one can directly calculate the redshift. Spectroscopic redshifts are generally very accurate, with uncertainties often less than 1%, but spectroscopy requires sufficient signal to resolve the spectrum, which means it works only for relatively bright objects or requires very long exposures, and it can observe only one or a small number of objects at a time, making it inefficient for surveying large numbers of faint galaxies. Photometric redshift estimation, by contrast, uses broadband imaging in multiple filters, each covering a range of wavelengths, and fits the observed brightness in each filter to model spectra at different redshifts. The idea is that the spectral energy distribution of a galaxy, the way its brightness varies with wavelength, depends on the redshift because features in the spectrum shift to longer wavelengths. For example, the Lyman break, a sharp drop in flux at wavelengths shorter than 121.6 nanometers in the rest frame due to absorption by neutral hydrogen, shifts to longer observed wavelengths as redshift increases. At Z equals 7, It appears at about 970 nanometers. At Z equals 10, at about 1,340 nanometers. By observing a galaxy through filters that sample different parts of the spectrum, one can identify where the Lyman break falls and infer the redshift. Similarly, the Balmer break at 365 nanometers rest frame and broader features like the overall slope of the continuum and the presence of emission or absorption bumps provide additional constraints. However, photometric redshifts are subject to degeneracies and systematic uncertainties. Different combinations of redshift, stellar age, star formation history, dust attenuation, and metallicity can produce similar observed colors, leading to ambiguity. For example, a galaxy that is very dusty and at moderate redshift might have similar colors to a dust-free galaxy at higher redshift, because dust reddens the light, shifting flux to longer wavelengths, mimicking the effect of redshift. This degeneracy can be broken with sufficient wavelength coverage and with spectroscopic confirmation, but in the absence of spectroscopy, photometric redshifts carry uncertainties that can be several tenths in Z, and occasionally catastrophic errors occur where the estimated redshift is completely wrong, off by factors of 2 or more, usually because a spectral feature was misidentified. In the early Webb observations, many of the candidate high redshift galaxies were identified photometrically, based on their colors in the near-infrared and mid-infrared filters. Some of these candidates were initially reported with redshifts as high as Z equals 12, 14, or even 16, which would place them at times when the universe was only 200 to 300 million years old. These reports generated significant excitement, but they also prompted caution, because photometric redshift estimates at such extremes are particularly uncertain, and follow-up spectroscopy is required to confirm. As spectroscopic follow-up has been obtained for a subset of these candidates, some have been confirmed at high redshift, validating the photometric estimates, while others have been revealed to be at lower redshift, often dusty galaxies at Z around 4 to 6, where dust and strong emission lines conspired to mimic the photometric signature of a much higher redshift. This process of confirmation and revision is normal in astronomy, but it is essential to the rewriting of the map, because the map can only be rewritten on the basis of secure measurements, not tentative candidates. The confirmed high redshift galaxies, those with spectroscopic redshifts above Z equals 8 or 9, exhibit properties that challenge the pre-Webb models in several specific ways. One of the most striking is their brightness. The observed flux from these galaxies, even accounting for the fact that they are very distant and therefore very faint in absolute terms, corresponds to intrinsic luminosities that are higher than expected for the halo masses available at those early times in the standard cosmological framework. In the prevailing model of structure formation, dark matter collapses into halos under gravity, and baryonic matter, ordinary matter made of protons, neutrons, and electrons, falls into those halos and cools, eventually forming stars and galaxies. The abundance of halos of different masses at different cosmic times is predicted by the cosmological model and has been calibrated by simulations and observations. At Z equals 10, the most massive halos that have collapsed are relatively small by present-day standards, with masses of perhaps a few times 10 to the 10th solar masses, and the efficiency with which baryons within those halos are converted into stars is expected to be limited by various feedback processes. Supernova explosions that heat and expel gas, radiation pressure from young stars, photoionization of gas by ultraviolet photons, and possibly feedback from accreting black holes. These feedback mechanisms regulate star formation and prevent all available gas from turning into stars quickly. Given these constraints, the models predicted that galaxies at Z equals 10 should have stellar masses of order 10 to the 8th or 10 to the 9th solar masses, corresponding to absolute magnitudes in the ultraviolet of about -18 to -20, which is faint, comparable to the Small Magellanic Cloud, a dwarf galaxy satellite of the Milky Way. What Webb is finding, in at least some cases, are galaxies at these redshifts with absolute magnitudes as bright as -20 to -22, which implies either significantly higher stellar masses, of order 10 to the 9th to 10 to the 10th solar masses, or extraordinarily high specific star formation rates of star formation per unit stellar mass, or a combination of both, or alternatively, that the light is not coming from ordinary stellar populations, but from something else, such as an active galactic nucleus powered by a supermassive black hole, or an exotic stellar population with an unusual initial mass function that produces more luminosity per unit stellar mass. To infer the stellar mass of a galaxy, astronomers fit models of stellar populations to the observed spectral energy distribution. These models assume a star formation history, how the rate of star formation has varied over time, and an initial mass function, which describes the relative number of stars formed at different masses. The initial mass function is critical because massive stars are much more luminous than low-mass stars but live much shorter lives. So the luminosity of a stellar population depends strongly on the recent star formation history and the fraction of massive stars. The standard initial mass function, often called the salpeter, or Krupa, or Chabrier, E.M.F., after the researchers who derived different versions, predicts that for every very massive star, there are many more low-mass stars, with the number of stars declining steeply with increasing mass. If the true initial mass function in these early galaxies is different, say top-heavy, with a higher fraction of massive stars, then a given luminosity would imply a lower total stellar mass, because more of the light is coming from the massive luminous stars rather than being shared across a large population of lower-mass stars. This is one way to reconcile bright galaxies with lower stellar masses, but it requires explaining why the initial mass function would be different in the early universe, and there is currently no strong independent evidence for such a difference, though it is plausible that the initial mass function could vary with metallicity, gas density, or turbulence. Another possibility is that the star formation is happening in an intense, short-lived burst, so the galaxy is caught at a moment when it is forming stars at an extremely high rate, and therefore very luminous. But the total stellar mass that has accumulated up to that point is still modest, because the burst has not been ongoing for long. In this scenario, the high luminosity reflects not a large mass but a high, instantaneous star formation rate, and the challenge for models becomes explaining why such intense bursts are common or long-lived enough to be observed frequently in the early universe, when feedback processes might be expected to quench star formation rapidly. Dust plays a crucial and complex role in these inferences. Dust consists of tiny solid particles, typically a fraction of a micron in size, composed of silicates, carbonaceous materials, and other compounds, formed in the atmospheres of evolved stars and in supernova ejetions, and then mixed into the interstellar medium. Dust absorbs ultraviolet and optical light from stars and re-emits that energy in the infrared, so a dusty galaxy appears fainter in the ultraviolet and brighter in the infrared than a dust-free galaxy with the same stellar population. The presence of dust therefore causes us to underestimate the ultraviolet luminosity if we observe only in the ultraviolet, or overestimate the stellar mass if we infer it from infrared luminosity without properly accounting for the dust emission. Conversely, if we assume a galaxy is dust-free when it is actually dusty, we will underestimate both its star formation rate and its stellar mass, because we will not account for the obscured ultraviolet light. Webb's infrared capability allows it to detect the rest frame optical and near-infrared light from high redshift galaxies, which is less affected by dust than ultraviolet light, and also to detect the dust emission itself if it is strong enough. Observations in the mid-infrared, particularly with MIRI, can directly measure the thermal emission from dust at rest frame wavelengths of several microns, which provides an independent constraint on the dust mass and temperature. What has been found in some of the early Webb observations is that certain high redshift galaxies show evidence of significant dust, more than was expected at such early times. Dust requires metals, elements heavier than hydrogen and helium, because dust grains are made of things like carbon, oxygen, silicon, magnesium, and iron, and those elements are produced in stars and dispersed by supernovae and stellar winds. In the first generation of stars, formed from primordial gas that contained essentially only hydrogen and helium left over from the Big Bang, there would be no dust. Dust appears only after the first stars have lived and died, enriching the interstellar medium with metals. The timescale for this enrichment depends on the star formation history and the efficiency of mixing, and models generally predict that substantial dust masses should build up only after a few 100 million years of star formation. Finding dusty galaxies at Z equals 9 or 10, corresponding to ages of 400 to 500 million years after the Big Bang, implies either that star formation and enrichment proceeded very efficiently in those galaxies, or that the dust formation mechanisms were more efficient than in the present-day universe, or that the galaxies are older than they appear, having begun forming stars even earlier. The spectral energy distributions of some of these galaxies show a shape that is consistent with a mature stellar population, not just young, blue stars, but also older, redder stars that have been around for several 100 million years. This is inferred from the presence of a Balmer break or a continuum slope that is redder than expected from purely young stellar populations. If confirmed, this would imply that these galaxies began forming stars at redshifts significantly higher than 10, perhaps at Z equals 15 or 20, corresponding to times less than 200 million years after the Big Bang, which would push the formation epoch back into a regime where the cosmological conditions were quite different, and where the first stars and the first metal enrichment must have occurred even earlier. Gravitational lensing provides a powerful tool for studying these distant galaxies in greater detail. Lensing occurs when a massive foreground object, such as a galaxy cluster, bends the spacetime around it, and light from a background source follows the curved spacetime, resulting in the image of the background source being magnified, distorted, and sometimes multiplied into multiple images. The magnification can be factors of 10 or even 100 in the most extreme cases, effectively providing a natural telescope that boosts the sensitivity and allows the detection of sources that would otherwise be too faint, and also increases the spatial resolution, allowing the internal structure of the background galaxy to be resolved. Webb has observed several galaxy clusters that act as gravitational lenses, and in the lensed fields, numerous highly magnified background galaxies have been detected, some at very high redshifts. The lensing magnification depends on the mass distribution of the foreground lens, which must be modeled. The lens model is constructed by identifying multiple images of the same background source and using the positions, shapes, and relative brightnesses of those images to constrain the mass distribution of the lens. However, lens modeling is complex and subject to uncertainties, particularly in the central regions of clusters where the mass distribution is irregular and dominated by dark matter with contributions from the galaxies themselves. Different lens models can produce different magnification factors for a given background source, sometimes differing by factors of 2 or more, and this uncertainty propagates into the inferred intrinsic properties of the source. For example, if the true magnification is 10 but the model estimates 20, then the intrinsic luminosity and stellar mass inferred for the source will be a factor of 2 too low. Systematic uncertainties in lens models are a recognized limitation, and cross-checking with multiple lens models and seeking spectroscopic confirmation of the source redshifts helps mitigate this, but it remains an important source of uncertainty in the rewriting of the map. The issue of selection effects is also critical and often underappreciated. When we observe a patch of sky and detect galaxies, we are selecting objects that meet certain criteria. They must be bright enough to be detected above the noise, they must have colors that distinguish them from foreground contaminants, and they must be spatially resolved or at least distinguishable from point sources like stars. These criteria introduce biases. For example, if we select galaxies based on their brightness in a particular filter, we will preferentially select galaxies that are luminous in that filter, which could be because they have high stellar masses, or high star formation rates, or particular stellar populations or dust properties that boost the flux in that filter. We will miss galaxies that are intrinsically fainter, or that have spectral energy distributions that do not stand out in our filters, or that are too compact and appear point-like and are therefore excluded as potential stars. The result is that the sample of galaxies we study is not a complete census of all galaxies at that redshift, but a biased subset, and the properties we infer for that subset may not be representative of the full population. Cosmic variance is another statistical limitation. Because we observe only a small patch of sky, the number of galaxies we detect at high redshift in that patch is subject to Poisson noise, the random statistical variation in small number counts, and also to clustering, because galaxies are not uniformly distributed but cluster together due to the gravitational influence of dark matter. If the patch of sky happens to intersect a region of above average density, we will detect more galaxies than average, and if it intersects a region of below average density, we will detect fewer. The amplitude of this cosmic variance depends on the volume surveyed and the clustering strength, and at high redshift, where the comoving volume corresponding to a given solid angle on the sky is smaller due to the geometry of the expanding universe, cosmic variance can be a significant effect. For rare, bright objects which are expected to reside in the most massive halos and therefore be strongly clustered, the uncertainty due to cosmic variance can be as large as or larger than the Poisson uncertainty, making it difficult to determine whether an apparent excess or deficit of such objects is a real feature of the galaxy population or a statistical fluctuation. These considerations mean that the rewriting of the map is not a simple matter of updating numbers, but requires careful statistical modeling that accounts for selection effects, cosmic variance, photometric redshift uncertainties, lens model uncertainties, and the degeneracies in interpreting spectral energy distributions. The revised map is being constructed through a combination of direct observations, simulations that model the galaxy formation process in detail and predict what should be observed under different assumptions, and statistical inference methods that compare the predictions to the data and adjust the model parameters to find the best fit. This process is iterative and ongoing, and the map is still being rewritten as more data accumulates, as spectroscopic confirmations are obtained, and as the models are refined. One specific relationship that is being revised is the stellar mass function at high redshift, which describes the number density of galaxies as a function of their stellar mass at a given cosmic time. Pre-Webb, the stellar mass function at z equals 9 or 10 was poorly constrained, but thought to decline steeply at high masses, with very few galaxies exceeding 10 to the 10th solar masses. Webb observation suggests that the high mass end of the stellar mass function may be higher than previously thought, meaning there are more massive galaxies at early times than the models predicted. This is sometimes phrased as an excess of massive galaxies, or an overabundance of bright galaxies, and it pressures the models because forming massive galaxies early requires either very efficient star formation, or early onset of star formation, or both, and it may require revisiting assumptions about feedback, about the efficiency of gas cooling, about the distribution of dark matter halos, or even about the cosmological parameters. Though changing the cosmology to produce more early structure would have wide-ranging implications that must be consistent with all other cosmological observables, such as the cosmic microwave background, and so far there is no compelling evidence that the cosmology itself needs to be revised, only that the astrophysics of galaxy formation may need adjustment. Another relationship being revised is the star formation rate density as a function of redshift, which is the total rate of star formation per unit comoving volume integrated over all galaxies as a function of cosmic time. This quantity is a key diagnostic of how the universe as a whole is converting gas into stars, and it is thought to have increased from very early times, peaked at around Z equals 2 to 3, corresponding to roughly 2 to 3 billion years after the Big Bang, and then declined to the present day. The shape of this curve, and in particular the level at early times, depends on the abundance and star formation rates of galaxies at high redshift. If Webb is finding that there are more galaxies, or more luminous galaxies, or higher inferred star formation rates at Z greater than 8 than expected, then the star formation rate density at those times must be revised upward, which in turn affects our understanding of how quickly the first stars and galaxies assembled, how much heavy element enrichment occurred, and how much ionizing radiation was produced. The epoch of reionization is directly connected to these considerations. After the Big Bang, the universe was hot and ionized, but as it expanded and cooled, the protons and electrons combined to form neutral hydrogen atoms, a process called recombination, which occurred at a redshift of about Z equals 1,100, roughly 380,000 years after the Big Bang. From that point until the formation of the first stars and galaxies, the universe was filled with neutral hydrogen gas, a period sometimes called the Dark Ages, because there were no luminous sources. The first stars, forming at redshifts estimated to be around Z equals 20 to 30 or even higher, emitted ultraviolet photons energetic enough to ionize hydrogen, and as more stars formed and more ionizing photons were produced, expanding bubbles of ionized gas grew around the sources and eventually overlapped, a process called reionization, which gradually converted the intergalactic medium from neutral back to ionized. Observations of the cosmic microwave background and of distant quasars suggest that reionization was complete by about Z equals 6, and that it was largely complete by Z equals 7 or 8. Though the exact timeline and the nature of the sources responsible, whether they were galaxies, or massive stars, or the first black holes, remain uncertain. The number and luminosity of galaxies at Z equals 8 to 12. The range Webb is probing directly affects the production rate of ionizing photons, and therefore the progress of reionization. If there are more bright galaxies than expected, they produce more ionizing photons, which can speed up reionization. However, the fraction of ionizing photons that escape from galaxies into the intergalactic medium, called the escape fraction, is also critical and uncertain. Stars produce ionizing photons, but those photons can be absorbed by neutral hydrogen within the galaxy itself, or by dust, and only the fraction that escapes contributes to reionizing the intergalactic medium. The escape fraction is observed to be low, typically a few percent in nearby galaxies, but it may have been higher in the early universe if galaxies were less dusty, more compact, or had different gas distributions. Webb's observations, by characterizing the properties of high redshift galaxies in detail, provide constraints on their ionizing photon production, and, combined with other probes of reionization such as observations of the Lyman alpha forest in quasar spectra and measurements of the intergalactic medium's ionization state, help refine the timeline and source contributions. Morphologically, the galaxies Webb is observing at high redshift show a range of structures. Some appear compact, almost point-like, which could indicate either that they are genuinely very small, with sizes of only a few hundred parsecs, or that the star formation is concentrated in a compact core, or that the resolution is insufficient to resolve more extended structure. Other galaxies appear more extended, with irregular or clumpy morphologies, and in some cases, there are hints of multiple components or substructure, which could indicate ongoing mergers or the presence of multiple star-forming clumps within a single halo. The morphologies provide clues about the formation process. Compact, high-density starbursts might form from gas-rich mergers or from cold streams of gas funneling directly into the center of a halo, while more extended, irregular structures might indicate more gradual accretion or less violent assembly. The fact that some high-redshift galaxies are already showing signs of structure, rather than being completely amorphous or chaotic, suggests that processes such as disk formation, bar instabilities, or spiral arm development may be operating earlier than expected, though interpreting morphology at such faint levels and at the resolution limits of the telescope is challenging, and small differences in noise or image processing can alter the apparent morphology. The chemical composition of these galaxies, their metallicity, is another dimension of the map being rewritten. Metallicity refers to the abundance of elements heavier than helium, often quantified as the ratio of oxygen to hydrogen or iron to hydrogen relative to the solar values. In the early universe, the gas from which stars formed was metal-poor, with metallicities much lower than the Sun, and as stars formed, evolved, and exploded, they enriched the interstellar medium with metals, gradually increasing the metallicity. The metallicity of a galaxy at a given time reflects its star formation history and the efficiency of mixing and retaining metals. Observing metallicity at high redshift requires detecting emission lines from ionized gas, such as the oxygen lines at rest frame wavelengths around 372, 500, and 5007 angstroms, and measuring the relative strengths of different lines, which depend on the ionization state and the metallicity. Webb's spectroscopic capabilities, particularly with the NIR SPEC instrument, allow these lines to be measured for high redshift galaxies, and early results indicate a range of metallicities, with some galaxies showing surprisingly high values for their redshift, approaching or exceeding 10% of solar metallicity at Z equals 8 or 9. High metallicity at early times again implies efficient and early enrichment, and it affects the cooling of gas, the formation of dust, and the types of stars that form, because metals provide additional cooling pathways for gas and seed the formation of dust. The interpretation of metallicity measurements is not straightforward, because the inferred metallicity depends on assumptions about the ionization state of the gas, the temperature, the density, and the shape of the ionizing spectrum, all of which are uncertain and must be modeled. Different diagnostic methods, using different line ratios, can give somewhat different metallicity estimates, and systematic uncertainties of a factor of 2 or more are common. Additionally, the metallicity measured from emission lines reflects the conditions in the ionized gas regions, which may not be representative of the galaxy as a whole if there is significant variation in metallicity across different regions, or if the star-forming regions are preferentially metal-rich or metal-poor. Despite these uncertainties, the general trend that some high-redshift galaxies are more metal-rich than expected adds to the pressure on models, because it suggests that the chemical evolution proceeded rapidly, which is consistent with the indications of high stellar masses and dust content at early times. Active galactic nuclei, powered by accretion onto supermassive black holes, are another potential contributor to the brightness of high redshift galaxies, and another factor in rewriting the map. An accreting black hole can be extraordinarily luminous, outshining the entire stellar population of a galaxy, and if a significant fraction of the high redshift objects identified by Webb are actually AGN rather than purely stellar systems, then the inferred stellar masses and star formation rates would be overestimated, because much of the light would be coming from the AGN rather than from stars. Distinguishing AGN from star-forming galaxies can be done through several methods. AGN tend to have very compact point-like cores. They emit strongly in the X-rays. Their infrared spectra may show hot dust emission with a characteristic spectral shape, and their emission line ratios differ from those of star-forming regions because the gas is ionized by a harder radiation field from the AGN. Webb's instruments can provide some of these diagnostics, particularly the infrared spectral features and emission line ratios, and early studies have identified a few candidate AGN at high redshift. But for most of the high redshift galaxies, the evidence so far is more consistent with stellar-dominated systems than AGN, though the possibility of lower luminosity AGN contributing some fraction of the light cannot be ruled out. The existence of supermassive black holes at very high redshift is itself a puzzle related to the rewriting of the map. Supermassive black holes with masses of 1 billion solar masses or more have been observed in quasars at redshifts as high as Z equals 7.5, corresponding to less than 700 million years after the Big Bang. Growing a black hole to such a mass in such a short time requires either very high accretion rates, close to the Eddington limit where radiation pressure from the accreting material nearly balances gravity, sustained over most of the available time, or the black holes must have started from unusually massive seeds, of order 10,000 to 1 million solar masses, rather than from the remnants of the first stars, which would have been only a few tens to 100 solar masses. The formation of such massive seeds and the environments that allow rapid black hole growth are active areas of research, and the discovery of AGN or massive black holes at even higher redshifts with Webb would further constrain these models. The interplay between black hole growth and galaxy growth is also important, because feedback from AGN can regulate star formation, either by heating and expelling gas or by compressing gas and triggering star formation, and understanding this coevolution is part of understanding the formation of galaxies. The point spread function of the telescope, which describes how light from a point source is spread out in the image due to the finite size of the telescope aperture and optical imperfections, is another technical consideration that affects the interpretation of observations. For Webb, the point spread function in the near-infrared has a width of about 0.1 arcseconds, which corresponds to physical sizes of a few hundred parsecs at Z equals 10, depending on the exact cosmology. This means that galaxies smaller than this size cannot be spatially resolved and will appear point-like, and even for somewhat larger galaxies, the observed structure is a convolution of the true structure with the point spread function, which blurs and smears the image. Deconvolving the point spread function to recover the true structure is possible in principle, but requires careful modeling and is subject to noise and artifacts, particularly for faint objects. The point spread function also has a wavelength dependence, being broader at longer wavelengths, which means that observations in the mid-infrared with MIRI have coarser resolution than near-infrared observations with NIRCam, and this affects the ability to measure sizes, morphologies, and to separate close sources. Background subtraction is a critical step in the data reduction process because the detectors record not only the light from distant galaxies, but also background contributions from zodiacal light, which is sunlight scattered by dust in the solar system, from faint unresolved galaxies that are too faint to be individually detected, but collectively contribute a diffuse glow, from stray light within the instrument, and from the dark current and red noise of the detectors themselves. The background must be estimated and subtracted to isolate the signal from the target galaxies, and this is typically done by measuring the flux in regions of the image that do not contain bright sources, or by constructing a background model based on calibration observations. However, the background is not perfectly uniform and can vary across the field of view and with time, and imperfect background subtraction can leave residuals that appear as spurious signals or that suppress real faint signals, leading to errors in the photometry and the inferred properties of sources. For deep observations, where the signal from faint galaxies can be comparable to the background variations, this is a significant concern, and careful analysis and cross-checks are required to ensure that the results are robust. Cosmic rays, high-energy particles from space, strike the detectors and create bright streaks or spikes in individual images. These must be identified and removed, typically by combining multiple exposures and using statistical methods to reject outliers. If cosmic rays are not removed effectively, they can be mistaken for faint sources or can corrupt the photometry of real sources, and this is another source of potential error in the data. The calibration of the detectors, including the gain, the flat field response, the linearity, and the wavelength calibration for spectra, also introduces uncertainties. The calibration is performed using observations of standard stars and other reference sources, and the accuracy is limited by the signal-to-noise of those observations and by the stability of the instrument over time. Calibration errors propagate into uncertainties in the measured fluxes and colors, and hence into the derived properties. The interpretation of colors and spectral energy distributions relies on models of stellar populations, which are computed by taking initial mass functions, star formation histories, metallicities, and ages, and combining the spectra of many individual stars to produce the integrated spectrum of a stellar population. These models are based on stellar evolution theory and empirical libraries of stellar spectra, and they involve assumptions and approximations. For example, the treatment of binary stars, which can affect the colors and luminosities of stellar populations through mass transfer and mergers, is often simplified. The treatment of dust attenuation uses empirical or theoretical dust attenuation curves, such as the Calzetti law, or the SMC or LMC extinction curves, which describe how dust absorbs and scatters light as a function of wavelength. But the actual dust properties in high redshift galaxies may differ from these templates, introducing systematic uncertainty. The emission from ionized gas, which produces emission lines that can contribute significantly to the broadband fluxes in certain filters, is sometimes included in the models and sometimes not, and the strength of the emission lines depends on the star formation rate, the ionization parameter, and the metallicity, adding another layer of complexity. The stellar mass estimates derived from fitting these models to observed spectral energy distributions can vary by factors of 2 to 3, depending on the assumptions about the star formation history, the initial mass function, the dust attenuation, and the stellar population models used. This degeneracy is well known in the field and is a major source of systematic uncertainty in constructing the stellar mass function and in assessing whether the observed galaxies are truly more massive than models predict. Ideally, additional constraints from spectroscopy, such as the detection of absorption lines that indicate the presence of older stellar populations, or the measurement of star formation rates from emission lines that can be compared to the star formation rates inferred from the ultraviolet continuum, help break the degeneracies. But even with spectroscopy, some uncertainty remains. The timescales involved in galaxy formation at high redshift are short by present-day standards, but can still span hundreds of millions of years, which is a significant fraction of the age of the universe at those times. For example, at z equals 10, the universe is about 470 million years old. So if a galaxy has a stellar population with an age of 200 million years, it means that galaxy began forming stars at around z equals 14 or 15, which is pushing into the regime where the first stars are expected to form. The inferred ages of stellar populations depend on features in the spectral energy distribution, particularly the Balmer break and the overall color, but also on the assumption of when star formation began and how it evolved over time. A galaxy with a constant star formation rate over time will have a different spectral energy distribution than a galaxy with a declining star formation rate, or one that experienced a recent burst. And without spectroscopic information to resolve these ambiguities, the inferred ages are uncertain. The concept of downsizing, which refers to the observation that more massive galaxies tend to have older stellar populations and to have completed most of their star formation earlier than less massive galaxies, is a feature of the galaxy population in the local universe and at intermediate redshifts, but it is not clear whether downsizing applies at the highest redshifts. If the high redshift galaxies observed by Webb are indeed massive and already contain old stellar populations, it would suggest that massive galaxy formation can begin very early, which is somewhat in tension with the hierarchical picture where massive galaxies build up through mergers of smaller systems over time. However, the two pictures are not mutually exclusive, because a galaxy can experience a phase of intense star formation early on, building up a substantial stellar mass in a short burst, and then grow further through mergers, so the old stellar population reflects the early phase, and subsequent growth adds younger populations. The role of mergers in driving star formation and building stellar mass is another aspect of the map being rewritten. In the hierarchical model, mergers are expected to be common at high redshift because the universe is denser and halos are closer together, and major mergers, collisions between galaxies of comparable mass, can trigger intense starbursts by driving gas into the central regions where it collapses and forms stars. However, mergers also disrupt the structure of galaxies, and the remnants of major mergers tend to be elliptical or spheroidal rather than disk-like, so the presence of disk-like or irregular structures at high redshift might suggest that smooth accretion or minor mergers, where a small galaxy is absorbed by a larger one, are more important than major mergers at early times. Observations of the frequency and properties of mergers at high redshift are difficult because of the faint fluxes and small angular sizes, but Webb's resolution and sensitivity are beginning to provide statistical samples that can test these predictions. The stellar initial mass function itself, which we have mentioned several times, is one of the deep assumptions underlying almost all inferences in extragalactic astronomy, and if it varies with environment, redshift, metallicity, or other factors, then the entire framework for inferring stellar masses, star formation rates, and chemical evolution would need revision. There are theoretical reasons to suspect that the initial mass function might be different in the early universe. The gas from which stars formed was more pristine, with lower metallicity, and metal-poor gas cools less efficiently, which could lead to higher characteristic fragmentation masses and a top-heavy initial mass function with more massive stars. Conversely, the gas might have been more turbulent, which could affect fragmentation in the opposite direction. Observational tests of the initial mass function at high redshift are difficult because they require measuring quantities that are sensitive to the low mass end of the mass function, such as the mass-to-light ratio inferred from dynamics, which is not feasible for distant galaxies, or the relative strengths of spectral features that depend on the ratio of giant stars to dwarf stars, which requires high-quality spectroscopy. Some studies have suggested variations in the initial mass function in local galaxies, particularly in the centers of massive elliptical galaxies, but the evidence is debated, and extrapolating to high redshift conditions is speculative. The feedback processes that regulate star formation are complex and operate on a range of scales. Stellar feedback refers to the energy and momentum injected into the interstellar medium by stars through radiation pressure, stellar winds, and supernova explosions. Massive stars, which are very luminous and short-lived, emit intense ultraviolet radiation that ionizes surrounding gas and exerts radiation pressure, and when they explode as supernovae, they release enormous amounts of energy of order 10 to the 51st ergs in a matter of seconds, driving shocks that heat and accelerate gas. If this feedback is efficient, it can expel gas from the galaxy, reducing the reservoir available for future star formation, and can also heat the remaining gas, reducing its density and making it harder for it to collapse and form stars. The efficiency of feedback depends on the distribution of stars, the density and structure of the gas, the escape of radiation and hot gas from the galaxy, and the presence of magnetic fields and cosmic rays, which can provide additional pressure support. Simulations of galaxy formation include prescriptions for stellar feedback, But the detailed physics is complex and operates on scales below the resolution of the simulations, so the prescriptions are based on subgrid models that capture the average effects but may not accurately represent all situations. Active galactic nucleus feedback, which we have mentioned in the context of supermassive black holes, operates similarly but on potentially larger scales and with higher energy inputs. An actively accreting supermassive black hole can release energy at rates comparable to or exceeding the total luminosity of the stellar population, and this energy can couple to the surrounding gas, driving outflows at speeds of thousands of kilometers per second that extend far beyond the galaxy, into the circumgalactic medium and even into the intergalactic medium. These outflows can remove gas, preheat gas to prevent it from cooling and forming stars, and in some cases, compress gas and trigger star formation in a mode called positive feedback. The interplay between star formation and black hole growth, mediated by these feedback processes, is thought to be responsible for the observed correlations between black hole mass and galaxy properties, such as the mass of the stellar bulge, and for the quenching of star formation in massive galaxies. But the details are still being worked out, and the role of AGN feedback at high redshift, when black holes were still growing and galaxies were still assembling, is particularly uncertain. The intergalactic medium, the diffuse gas between galaxies, also plays a role in regulating galaxy formation. Gas falls into dark matter halos from the intergalactic medium, and the rate at which gas is accreted depends on the halo mass, the temperature and density of the intergalactic medium, and the presence of ionizing radiation that can photoionize the gas and increase its pressure, making it harder for low-mass halos to accrete. After reionization, the intergalactic medium is ionized and heated to temperatures of tens of thousands of Kelvin, and this heating suppresses gas accretion onto halos with masses below a certain threshold, sometimes called the filtering mass, of order 10 to the 9th to 10 to the 10th solar masses, depending on the timing and spectrum of reionization. This is one reason why models predict that low-mass galaxies should be less common after reionization than before, but Webb's observations are finding low-mass galaxies at redshifts both before and after reionization, and the comparison between the two regimes will help constrain the effects of reionization on galaxy formation. The large-scale structure of the universe, the cosmic web of filaments, sheets, and voids, traced by the distribution of dark matter and galaxies, also influences galaxy formation by determining where gas is located and how it flows. Galaxies tend to form at the nodes and along the filaments of the cosmic web, where dark matter halos are most concentrated, and gas flows along filaments toward the halos, a process called cold-mode accretion. In the early universe, when the density was higher, the cosmic web was more tightly packed, and accretion rates were higher, which may have facilitated rapid galaxy growth. Simulations of structure formation predict the evolution of the cosmic web and the halo mass function, and by comparing the observed distribution of galaxies with these predictions, we can test the cosmological model and infer the relationship between galaxies and dark matter halos, often parameterized as the stellar mass to halo mass relation, or the star formation efficiency as a function of halo mass. Adjustments to this relationship are one of the ways models are being revised in response to Webb's observations. The concept of the halo occupation distribution is a statistical tool used to connect the observed galaxy distribution to the underlying dark matter halo distribution. It describes the probability that a halo of a given mass hosts a certain number of galaxies, and it can be constrained by observations of galaxy clustering. If the halo occupation distribution at high redshift is different from what models predict, for example, if halos are hosting more massive galaxies or more galaxies per halo than expected, it indicates that the efficiency of galaxy formation is higher, which again pressures the models and contributes to the rewriting of the map. Measuring the clustering of high redshift galaxies requires large statistical samples, because clustering is a second-order effect, depending not just on the number of galaxies, but on their spatial correlations, and Webb's deep fields, while very deep, cover relatively small areas, so the clustering measurements are subject to large uncertainties and cosmic variance. Wider area surveys at high redshift, either with Webb or with future missions, will improve these constraints. The look-back time corresponding to different redshifts depends on the cosmological parameters, and while those parameters are now well measured, small uncertainties in them propagate into uncertainties in the ages of the universe at different redshifts. The Hubble constant, which sets the current expansion rate, is currently subject to a tension between measurements from the cosmic microwave background, which favor a value around 67 kilometers per second per megaparsec, and measurements from distance ladders using supernovae and Cepheid variables, which favor a value around 73 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, is not yet resolved and may indicate new physics or systematic errors in one or both methods. The value of the Hubble constant affects the inferred distances and ages, so if it is higher, then the universe is younger at a given redshift, and the time available for galaxies to form is shorter, which would make the early appearance of massive galaxies even more challenging to explain. Conversely, if the Hubble constant is lower, there is more time, easing the tension slightly. However, the magnitude of the Hubble tension corresponds to only about a 10% difference in the age of the universe at high redshift, which is not large enough to resolve the apparent overabundance of massive galaxies by itself. So, even if the Hubble tension were resolved in favor of a lower value, the need to revise galaxy formation models would remain. Dark energy, the component of the universe that drives accelerated expansion, does not significantly affect the expansion history at high redshift, because dark energy only becomes dynamically important at later times, roughly around z equals 1 or lower. At high redshift, the universe is matter-dominated, meaning the expansion is governed primarily by the matter density, both dark matter and baryons. Therefore, uncertainties in the dark energy equation of state do not strongly impact the interpretation of Webb's high redshift observations, and the rewriting of the map is not connected to dark energy physics, but rather to the astrophysics of how matter collapses, cools, and forms stars within the framework of the standard cosmological model. Baryonic acoustic oscillations, the imprint of sound waves in the early universe on the large-scale structure, provide a standard ruler that can be used to measure the expansion history. But at high redshift, these features are difficult to detect because the surveys do not yet cover large enough volumes, and the signal is diluted by the small number of galaxies. Future surveys with larger samples of high redshift galaxies may detect baryonic acoustic oscillations and provide independent constraints on the cosmology, which would help confirm or refine the framework within which galaxy formation is being studied. The process of reionization, which we have touched on, is not instantaneous but extended over a range of redshifts, and the ionized regions grow and merge over time, creating a complex, inhomogeneous ionization field. The morphology of the ionization field depends on the distribution and luminosity of sources, the clumpiness of the intergalactic medium, and the recombination rate of ionized gas. Observations of the 21-centimeter line of neutral hydrogen, which corresponds to a hyperfine transition in the ground state of hydrogen, are expected to provide tomographic maps of the ionization field during reionization, but these observations are extremely challenging due to foreground contamination from our galaxy and from radio sources, and no definitive detection of the 21-centimeter signal from reionization has been made yet. When such observations become available, they will provide a complementary view of the early universe and help connect the galaxy population observed by Webb to the reionization process. The thermal history of the intergalactic medium is also connected to reionization and to the energy input from galaxies and AGN. The temperature of the intergalactic medium after reionization depends on the spectrum of ionizing radiation and on the subsequent heating by photoionization and structure formation shocks. Measurements of the temperature are made using the Lyman alpha forest, the absorption features in quasar spectra, caused by neutral hydrogen along the line of sight, and the width of the absorption lines depends on the temperature. These measurements indicate that the intergalactic medium was heated to tens of thousands of Kelvin during reionization, consistent with photoionization, and the temperature evolves with redshift as the universe expands and cools. The details of this thermal history provide constraints on the timing and sources of reionization and connect back to the properties of the galaxy population. The helium reionization, which occurs at lower redshift, around Z equals 3 to 4, when the ultraviolet radiation from quasars becomes energetic enough to doubly ionize helium, is a separate but related process. Helium has a higher ionization potential than hydrogen, requiring photons with energies above 54 electron volts to ionize He plus to He double plus, and such photons are predominantly produced by quasars rather than by stars. The study of helium reionization provides information about the quasar population and the evolution of the ultraviolet background, and it is another piece of the larger picture of how radiation from astrophysical sources shapes the intergalactic medium. The metallicity of the intergalactic medium, which can be measured from absorption lines in quasar spectra, provides information about the history of metal ejection from galaxies. Supernova-driven winds and AGN-driven outflows transport metals from galaxies into the circumgalactic medium and intergalactic medium, enriching the diffuse gas. The metallicity of the intergalactic medium at different redshifts reflects the cumulative history of star formation and feedback, and it is related to the metallicity of galaxies, though the relationship is complex because not all metals produced in galaxies are ejected, and the ejected metals may be preferentially stripped from low-mass galaxies due to their shallower gravitational potentials. Webb's measurements of galaxy metallicities and the inferred metal production rates can be compared to the observed intergalactic medium metallicity to assess the consistency of the overall picture of metal enrichment. The star formation efficiency, defined as the ratio of the star formation rate to the gas accretion rate or to the gas mass, is a key parameter in models, and adjusting this efficiency is one of the main ways models can be tuned to match observations. If the efficiency is higher, more of the accreted gas is converted into stars rather than being expelled or remaining as gas, and galaxies grow more massive more quickly. However, the efficiency cannot be arbitrarily high, because observations of the present-day universe indicate that only a small fraction, typically a few percent of the baryons in the universe are in stars, with the rest remaining in gas, either within galaxies or in the intergalactic medium. This implies that feedback has been effective at preventing gas from forming stars efficiently, and raising the efficiency at early times to match the Webb observations requires explaining why feedback was less effective then, or why the conditions were such that star formation proceeded faster despite feedback. One possibility is that gas inflow rates were much higher at early times, overwhelming feedback, so even if feedback expelled some fraction of the gas, the remaining fraction was still sufficient to sustain high star formation rates. Another possibility is that the geometry of gas accretion was different, with cold, dense streams delivering gas directly to the central regions of galaxies, bypassing the hot halo where feedback energy would be deposited. Simulations that include these cold streams show that they can sustain high star formation rates in high redshift galaxies, and this may be part of the explanation for the observed properties. However, the detailed physics of cold streams, including their stability, their ability to penetrate through the halo, and their interaction with feedback, is still being studied. The mass loading factor, which quantifies the ratio of the mass outflow rate to the star formation rate, is another parameter that affects the efficiency. If the mass loading factor is high, then feedback is expelling gas at a rate much larger than the rate at which stars are forming, which limits the buildup of stellar mass. If the mass loading factor is low, feedback is less effective and more stellar mass accumulates. Observational measurements of outflows in high redshift galaxies are difficult because outflows are typically detected through blue-shifted absorption lines in spectra, indicating gas moving toward the observer, or through extended emission in certain lines, indicating shocked or ionized gas being expelled, and such observations require high-quality spectroscopy and high spatial resolution. Webb's spectroscopic capabilities are beginning to enable these measurements for a subset of high redshift galaxies, and the results will provide direct constraints on feedback efficiency. The concept of quenching, the cessation of star formation, is mostly relevant for later times and more massive galaxies, but even at high redshift, some galaxies may experience temporary or permanent quenching if feedback is strong enough to expel or heat all the available gas, or if gas accretion is somehow shut off. Quenched galaxies at high redshift would appear red, with little ongoing star formation, and they would be detectable by their spectral energy distributions, which would lack the blue continuum and strong emission lines characteristic of star-forming galaxies. Searches for quenched galaxies at high redshift have been conducted, and a few candidates have been identified, but they are rare, which is consistent with the expectation that most galaxies at early times are still actively forming stars. The existence of even a few quenched galaxies at high redshift would be interesting because it would indicate that feedback can be effective early on, at least in certain environments or for certain galaxies. The role of environment in galaxy formation becomes more important at later times as galaxies cluster together into groups and clusters, and as processes like ram pressure stripping, where the hot gas in the cluster strips gas from infalling galaxies, and galaxy harassment, where repeated close encounters disturb galaxies and affect their star formation, become relevant. At high redshift, the universe is less clustered, and these environmental effects are expected to be less important, but overdense regions that are the progenitors of present-day clusters do exist, and the galaxies in those regions may have different properties due to their higher merger rates or different gas accretion histories. Identifying protoclusters at high redshift and studying the galaxies within them is another area where Webb is contributing, by finding concentrations of galaxies at similar redshifts and characterizing their properties relative to field galaxies. The dust temperature in high redshift galaxies is another observable that constrains the star formation and interstellar medium properties. Dust is heated by absorbing ultraviolet and optical photons from stars, and it re-emits that energy in the infrared, with a spectrum that depends on the dust temperature, which typically ranges from a few tens of Kelvin for cold dust in quiescent regions to a few hundred Kelvin for hot dust, near intense star formation, or AGN. The observed infrared spectral energy distribution can be fit with models of dust emission to infer the dust temperature and mass, and the dust mass in turn provides a lower limit on the metal mass, because dust is made of metals. Webb's mid-infrared observations with MIRI are sensitive to rest frame infrared emission from high redshift galaxies and can detect or constrain the dust emission, and early results suggest that some galaxies have warm dust, consistent with intense star formation or compact geometry, while others have cooler dust or are undetected in the mid-infrared, indicating lower dust masses or temperatures. Polycyclic aromatic hydrocarbons, or PAHs, are large organic molecules composed of carbon and hydrogen, and they are a component of interstellar dust. PAHs have characteristic emission features in the mid-infrared at wavelengths around 3.3, 6.2, 7.7, 8.6, and 11.3 microns, and these features are commonly observed in nearby star-forming galaxies. The presence or absence of PAH features in high redshift galaxies can indicate the maturity of the interstellar medium, because PAHs are thought to form in the atmospheres of evolved carbon-rich stars or in the interstellar medium after sufficient carbon has been produced. So detecting PAH emission at high redshift would suggest that the chemical enrichment has progressed far enough to produce these molecules. Early Webb spectroscopy has detected PAH emission in some high redshift galaxies, which is somewhat surprising given the young ages and low metallicities expected, and it adds to the picture of rapid enrichment and dust formation. The rest frame optical emission lines such as H-alpha, H-beta, the oxygen lines, and others are powerful diagnostics of star formation rate, metallicity, ionization state, and the presence of AGN. These lines are redshifted into the near-infrared for high redshift galaxies, and Webb's NIRSpec instrument, with its multi-object spectroscopy capability and its high sensitivity, is designed to observe these lines for large samples of galaxies. The line ratios, such as the ratio of O3 5007 to H-beta, or N2 6584 to H-alpha, place galaxies on diagnostic diagrams like the BPT diagram, which separates star-forming galaxies from AGN based on the ionization mechanisms. Early spectroscopic surveys with Webb have measured these line ratios for dozens to hundreds of galaxies at redshifts from 1 to beyond 8. And the results show that the line ratios evolve with redshift, with high redshift star-forming galaxies having higher ionization parameters and harder ionizing spectra than local galaxies, which may be due to lower metallicities, higher electron densities, or the prevalence of massive stars with harder radiation fields. The electron density of ionized gas in star-forming regions can be inferred from the ratio of certain emission lines that are density-sensitive, such as the OII doublet at 3,727 and 3,729 angstroms, or the SII doublet at 6,717 and 6,731 angstroms. Higher electron densities correspond to more compact star-forming regions, and some high redshift galaxies show evidence of very high electron densities, in excess of 1,000 per cubic centimeter, compared to typical values of 100 to a few hundred in local galaxies. High densities could indicate that star formation is concentrated in very compact regions, which would be consistent with the compact sizes inferred from imaging, and they would also affect the cooling and the inferred star formation rates because higher densities allow for more efficient cooling and potentially higher star formation efficiencies. The Lyman alpha line, the transition from the first excited state to the ground state of hydrogen, is a resonant line that is very strong in star-forming galaxies, and it was widely used as a tracer of high redshift galaxies before Webb, through narrowband imaging surveys and spectroscopy. However, Lyman alpha is easily absorbed by neutral hydrogen, so its visibility depends on the ionization state of the intergalactic medium and on the distribution of neutral hydrogen within and around the galaxy. During the epoch of reionization, the intergalactic medium is partially neutral, and Lyman alpha photons from galaxies are scattered and absorbed, reducing the observed Lyman alpha luminosity or shifting the line profile. The fraction of galaxies showing strong Lyman alpha emission decreases at higher redshifts, which is interpreted as evidence for increasing neutral fractions in the intergalactic medium, and this evolution provides a probe of the reionization timeline. Webb's spectroscopic observations can detect Lyman alpha in high redshift galaxies and measure its strength and profile, complementing earlier studies and providing a cross-check on photometric redshifts, because the presence or absence of Lyman alpha can help distinguish high redshift galaxies from lower redshift interlopers. The Lyman alpha forest, which we mentioned earlier, is seen in the spectra of bright background sources like quasars, and it consists of a series of absorption lines blueward of the quasar's Lyman alpha emission line, caused by intervening clouds of neutral hydrogen at various redshifts along the line of sight. The statistics of the Lyman alpha forest, the number, strength, and width of the absorption lines, provide information about the density, temperature, and ionization state of the intergalactic medium as a function of redshift. At very high redshift, approaching and during reionization, the Lyman alpha forest becomes increasingly opaque, eventually reaching a Gunn-Peterson trough, where nearly all flux blue ward of Lyman alpha is absorbed, indicating a significant neutral fraction. The exact redshift at which the Gunn-Peterson trough appears depends on the timing of reionization, and observations have found it beginning around Z equals 6, with increasing opacity at higher redshifts, consistent with reionization being completed by around Z equals 6 to 7, and the neutral fraction rising at earlier times. The concept of look-back time versus cosmic time is important for clarity. Look-back time is the time elapsed between the observation, now, and the emission of the light, so it is the age of the universe now minus the age of the universe at the redshift of the source. Cosmic time is the time since the Big Bang, so the age of the universe at a given redshift. When we say a galaxy at Z equals 10 is observed at a look-back time of about 13.3 billion years, we mean the light has been traveling for 13.3 billion years, and the universe was about 470 million years old when the light was emitted. The distinction matters because when we talk about the properties of galaxies at a certain redshift, we mean their properties at the cosmic time corresponding to that redshift, not at the present time. The comoving distance, another distance measure used in cosmology, accounts for the expansion of the universe and represents the distance to an object in coordinates that expand with the universe. So the comoving distance to a given object does not change with time, whereas the physical distance increases as the universe expands. Comoving distance is used to calculate volumes for determining number densities of galaxies, and it is related to redshift through the integral of the inverse of the Hubble parameter over redshift. The distinction between comoving and physical distances is important when comparing observations at different redshifts and when computing densities and clustering statistics. The angular diameter distance is the distance measure that relates the physical size of an object to its observed angular size. In an expanding universe, the angular diameter distance does not increase linearly with redshift. It reaches a maximum and then decreases at very high redshift, meaning that objects at extremely high redshift can actually have larger angular sizes for a given physical size than objects at intermediate redshift. This is a consequence of the fact that light from very high redshift was emitted when the universe was smaller and the photons have been traveling through expanding space, so the object subtends a larger angle on the sky. This effect is usually small but becomes relevant when interpreting the observed sizes of high redshift galaxies. The luminosity distance is the distance measure that relates the observed flux to the intrinsic luminosity, and it increases with redshift, approximately proportional to redshift at low redshift and more steeply at high redshift. The luminosity distance is what is used to compute absolute magnitudes from observed apparent magnitudes and redshifts, and it is larger than the comoving distance by a factor of 1 plus z, accounting for the redshift of the photons and the time dilation effect that reduces the observed flux. The surface brightness of a galaxy, which is its flux per unit solid angle on the sky, dims with redshift as 1 plus z to the fourth power, combining the reduction in flux due to luminosity distance, the dimming from redshift, the time dilation effect, and the angular size effect. This means that high redshift galaxies are much harder to detect in surface brightness than nearby galaxies of the same intrinsic brightness, and it is one reason why Webb's sensitivity is so important. It is not just about detecting faint point sources, but about detecting extended, low surface brightness structures. The photometric filters used by Webb's NIR-CAM and MIR-I instruments are carefully designed to sample key regions of the spectrum and to enable photometric redshift estimation and characterization of stellar populations. NIRCam has both wide filters, covering broad wavelength ranges for deep imaging, and medium-band filters, which cover narrower ranges and provide better spectral resolution, useful for identifying emission lines or refining photometric redshifts. MIRI has filters in the mid-infrared that are particularly sensitive to dust emission and to rest frame optical light from high redshift galaxies. The combination of filters allows multiband photometry that traces the spectral energy distribution from rest frame ultraviolet through optical to near-infrared and mid-infrared, providing a comprehensive view of the galaxy's light. The signal-to-noise ratio is a critical quantity in determining what can be measured reliably. It is defined as the signal, the number of photons detected from the source, divided by the noise, which includes photon noise from the source itself, photon noise from the background, and detector noise. The signal-to-noise ratio increases with the square root of the exposure time. So doubling the exposure time increases the signal-to-noise by a factor of 1.4, and reaching very high signal-to-noise ratios requires very long exposures. For faint sources near the detection limit, the signal-to-noise may be only a few, meaning the detection is only marginally significant, and careful statistical treatment is required to avoid spurious detections. For brighter sources, signal-to-noise ratios of tens or hundreds can be achieved, allowing precise photometry and detailed characterization. The concept of completeness in a survey refers to the fraction of objects of a given type that are detected. A survey is complete above a certain brightness threshold if essentially all objects brighter than that threshold are detected, but completeness drops for fainter objects as noise and confusion, overlapping sources, cause some objects to be missed. Understanding the completeness is essential for deriving number counts and luminosity functions, because if you do not account for the objects you are missing, you will underestimate the true abundance. Completeness is typically estimated through simulations, where artificial sources are added to the images and the detection algorithm is run to see what fraction of the artificial sources are recovered as a function of brightness, size, and color. The systematic uncertainties we have discussed, photometric redshift errors, stellar mass degeneracies, dust attenuation assumptions, lens model uncertainties, cosmic variance, selection effects, completeness, combine to create a web of interconnected uncertainties in the derived properties of high redshift galaxies. Quantifying these uncertainties rigorously requires careful error propagation and often Monte Carlo simulations where random realizations of the observations, consistent with the noise and systematic uncertainties, are generated and analyzed to produce distributions of inferred properties. The width of these distributions reflects the uncertainty, and the rewriting of the map must account for these uncertainties, distinguishing between robust results that are insensitive to the assumptions and tentative results that depend strongly on uncertain parameters. The comparison between different surveys and instruments is another important check. Webb's observations can be compared to earlier observations by Hubble, Spitzer, and ground-based telescopes for overlapping fields and redshift ranges, and consistency between the different data sets increases confidence in the results, while discrepancies point to systematic differences that need to be understood. For example, if Webb detects galaxies that were missed by Hubble, it may be because they are very red and faint in the optical, confirming that Webb's infrared capability is essential, or it may be because they are at higher redshift than Hubble could reach, extending the redshift frontier. If Webb measures different colors or sizes for galaxies also observed by Hubble, it may be due to differences in resolution, wavelength coverage, or calibration, and understanding these differences is important for combining data sets and for interpreting trends. The multi-wavelength approach, combining observations across the electromagnetic spectrum from radio to X-ray, provides the most complete picture of galaxies. Radio observations trace synchrotron emission from relativistic electrons, often associated with supernova remnants or AGN, and molecular line emission from cold gas, which is the fuel for star formation. Millimeter and submillimeter observations detect cold dust emission, particularly from very dusty, highly star-forming galaxies that are faint in the optical and near-infrared, but bright at longer wavelengths. X-ray observations detect hot gas in galaxy clusters, emission from supernova remnants, and the signatures of accreting black holes. Combining these observations with Webb's infrared data allows for a more complete understanding of the energy budget, the star formation activity, the black hole accretion, and the gas content. The future of the field involves not just Webb, but also upcoming facilities such as the Nancy Grace Roman Space Telescope, which will have a wide field of view and will conduct large-area infrared surveys, complementing Webb's deep but narrow observations, and the next generation of ground-based extremely large telescopes, such as the Extremely Large Telescope, the Giant Magellan Telescope, and the 30-meter telescope, which will have much larger collecting areas than Webb and will be able to obtain high-resolution spectroscopy of faint, high-redshift galaxies, further constraining their properties. The Square-Kilometer Array, a radio telescope under construction, will have the sensitivity to detect the 21-centimeter line from reionization and to study the cold gas in high-redshift galaxies. The combination of these facilities will provide a multifaceted view of the early universe and will continue the process of refining and rewriting the map. The iterative nature of science is important to emphasize. Observations lead to revised models, which make new predictions, which are tested by further observations, which lead to further revisions, in a cycle that gradually converges on a more accurate and complete understanding. The rewriting of the map is not a one-time event, but an ongoing process, and the current state reflects our best understanding given the data available so far, but it is certain to be refined as more data accumulates and as our analysis methods improve. The initial Webb observations have provided a first look at the high redshift universe with unprecedented clarity, and they have revealed surprises and tensions with models, but many of the sources identified in those early observations are still being followed up with spectroscopy, and the full implications are still being worked out. The community of researchers working on these problems is international and collaborative, with data being shared publicly and with multiple groups analyzing the same data sets using different methods and checking each other's results. This collaborative approach helps identify errors, test robustness, and build consensus around the key findings. Controversies and debates are a normal part of the process, and they drive progress by forcing careful examination of assumptions and methods. The rewriting of the map is the result of this collective effort, not the work of any single team or individual. The philosophical question of what it means to know something in science is also relevant here. We never have complete certainty. We have models that are consistent with observations to within uncertainties, and we have confidence levels that reflect the strength of the evidence. When we say the map is being rewritten, we mean that the previous models are no longer consistent with the new observations within the uncertainties, and adjustments are required, but those adjustments are themselves subject to uncertainties and are provisional, pending further tests. The process of science is one of successive approximations, each closer to the truth than the last, but never final. The concept of falsifiability, central to the scientific method, requires that models make predictions that can be tested and potentially disproven by observations. The galaxy formation models make predictions about the abundance, brightness, mass, and other properties of galaxies at different redshifts, and Webb's observations test those predictions. When the observations disagree with the predictions, the models must be revised, but the revisions must be done in a way that does not simply fit the new data while becoming inconsistent with other observations. This constraint, that models must be consistent with all available data across different regimes, limits the range of possible revisions and guides the development of more realistic models. The role of theory in guiding observations is also important. Theoretical predictions motivate which observations to make, what to look for, and how to interpret what is found. Conversely, unexpected observations, like those from Webb, challenge theory and drive theoretical development. The interplay between theory and observation is synergistic, with each informing and advancing the other. The rewriting of the map is driven by observations, but it is also guided by theoretical understanding of the physics of star formation, feedback, dark matter, and cosmology. The technical achievement represented by Webb is extraordinary. Launching a telescope with a mirror that unfolds in space, with a sunshield the size of a tennis court that deploys through a complex sequence of steps, with cryogenic instruments that must function flawlessly, and positioning it at L2, 1.5 million kilometers from Earth, where it cannot be serviced, required solving countless engineering challenges. The success of the mission is a testament to the dedication and ingenuity of the thousands of engineers, scientists, and support staff who worked on it over decades. The rewriting of the map is the scientific return on that investment, the new knowledge gained from the capabilities that were built. The infrared wavelength regime, which is Webb's domain, is essential not only for high redshift galaxies, but also for studying many other phenomena. The formation of stars in dusty molecular clouds, the atmospheres of exoplanets, the composition and temperature of brown dwarfs and cool stars, the structure of protoplanetary disks, the dust and gas in the interstellar medium, the nuclei of galaxies obscured by dust, and the spectra of solar system objects. Webb's science extends far beyond the high redshift universe, and its impact is being felt across all areas of astronomy. The rewriting of the map of the early universe is one part of a broader revolution in our understanding of the cosmos enabled by this instrument. The data archive from Webb, which is publicly accessible, will be a resource for astronomers for decades. As analysis techniques improve, as new theoretical insights emerge, and as complementary observations are made, the same datasets will be reanalyzed and will yield new discoveries. The value of the data extends beyond the initial publications, and the full scientific legacy of Webb will take many years to unfold. The map being rewritten now is based on the early data releases, but the map will continue to be revised and refined as more data is analyzed and as our understanding deepens. The timescale of star formation in individual galaxies, the duration of starbursts, the frequency of mergers, the timescale for feedback to expel gas, the timescale for gas to be accreted, and the timescale for chemical enrichment are all interconnected and depend on the physical conditions in the galaxy and its environment. Understanding these timescales is key to understanding how galaxies evolve, and Webb's observations, by providing snapshots of galaxies at different stages of their evolution, allow us to piece together the sequence of events. The challenge is that we do not observe individual galaxies evolving over time. We observe many different galaxies at different times and must infer the evolutionary pathways by comparing their properties. This is analogous to understanding human development by looking at photographs of many different people at different ages rather than following one person over their lifetime. The stochasticity of galaxy formation, the role of random events like the timing of mergers or the orientation of gas inflows, introduce a scatter in the properties of galaxies even if they form under similar conditions. This scatter is observed as a dispersion in the relationships between galaxy properties, such as the stellar mass versus star formation rate relation, and it reflects the diversity of formation histories. Models that include stochasticity can reproduce the observed scatter, and the amplitude of the scatter provides constraints on the strength of feedback and the variability of gas accretion. The initial conditions for structure formation, the tiny density fluctuations in the early universe that were amplified by gravity to form galaxies, are imprinted in the cosmic microwave background and are well measured. The subsequent growth of structure is deterministic given those initial conditions and the laws of physics, but the astrophysical processes, cooling, star formation, feedback, are complex and not determined purely by the initial conditions or the cosmology. So there is freedom in the models to adjust the efficiency of these processes, and that is where the rewriting of the map is occurring. The dark matter halo properties, such as their concentration, spin, and shape, affect how baryons behave within them, because these properties influence the gravitational potential, the angular momentum distribution, and the stability of gas orbits. Halos that are more concentrated have deeper potential wells and may retain gas more effectively against feedback, while halos with higher spin may form disks more easily. Simulations predict distributions of these properties based on the cosmological model, and by comparing the observed properties of galaxies to these predictions, we can test whether the mapping between halos and galaxies is consistent with the models. The assembly history of a halo, whether it grew smoothly through steady accretion or through a series of mergers, affects the properties of the galaxy it hosts. Halos that experienced recent major mergers may host disturbed, irregular galaxies with elevated star formation rates, while halos that have been quiescent for a long time may host more relaxed, evolved galaxies. The halo merger history is predicted by simulations and can be inferred statistically from observations of galaxy clustering and from the morphologies and kinematics of galaxies. The angular momentum of the gas, which comes from the tidal torques exerted by the large-scale structure during the halo's formation, determines whether the gas settles into a rotationally supported disk or falls radially into the center. Higher angular momentum leads to larger disk sizes, and the distribution of angular momentum within the gas determines the rotation curve and the radial distribution of star formation. Observations of the kinematics of high-redshift galaxies, using resolved spectroscopy to measure rotation velocities and velocity dispersions, provide tests of whether the gas is in a rotating disk, a turbulent dispersion-supported system, or a combination. Webb's spectroscopic capabilities, particularly with the integral field unit mode of NARSPEC, allow such kinematic studies for a subset of high-redshift galaxies, and early results show a mix of rotating and disordered systems, with some galaxies showing clear rotation and others showing complex or chaotic velocity fields. The connection between the scales we observe and the scales where the physical processes operate is mediated by our models and by the resolution of our observations. Webb can resolve scales down to a few hundred parsecs at high redshift, which is comparable to the size of giant molecular clouds where stars form, but the internal structure of those clouds, the fragmentation into individual star-forming cores, and the properties of individual stars are far below the resolution. We must rely on models of star formation and stellar populations, calibrated on nearby systems where we can observe these scales, and assume that the same physics applies at high redshift, though, as we have discussed, there may be differences due to different gas properties, metallicities, or radiation fields. The rewriting of the map involves not just changing numbers but also refining our conceptual framework, the way we think about galaxy formation. Before Webb, the narrative was largely one of gradual bottom-up assembly, with the first galaxies being small and faint, slowly growing over time through mergers and gas accretion, with massive galaxies emerging only at later times. Webb's observation suggests that this picture may need to include the possibility of more rapid early assembly, with some massive galaxies appearing earlier than expected, and with more diversity in formation pathways, including intense compact starbursts that build up significant stellar mass quickly. This does not invalidate the hierarchical framework, which is grounded in the cosmological model and is well supported by many observations, but it adds nuance and complexity, recognizing that the efficiency and timescales of galaxy formation are not uniform and depend on local conditions and on processes that are still being understood. The role of the first stars, often called population 3 stars, is another part of the story. These stars formed from primordial gas with no metals, and they are expected to have been very massive, possibly hundreds of solar masses, very hot, very luminous, and short-lived. They would have produced the first heavy elements, and their supernova explosions would have enriched the surrounding gas, enabling the formation of the next generation of stars with some metals, called population 2 stars. Population 3 stars have never been directly observed because they lived and died very early, and detecting them would require observing at redshifts perhaps as high as Z equals 20 to 30 or beyond, which is extremely challenging even for Webb. However, the integrated light from the first galaxies, which may contain significant contributions from population 3 stars if they are observed early enough, could have spectral features that reveal their presence, such as an extremely blue ultraviolet continuum or the absence of metal lines. Searching for such signatures in the faintest, highest redshift galaxies observed by Webb is an active area of research, and while no confirmed detection of population 3 stars has been made, the possibility remains that some of the objects observed may be dominated by or contain significant fractions of these primordial stars. The initial mass function for population 3 stars is expected to be different from that of present-day stars, likely shifted toward higher masses due to the higher characteristic Jeans mass in metal-free gas, which cools less efficiently and therefore has higher temperatures and pressures, leading to larger collapsing clumps. A top-heavy population 3 initial mass function would produce very high luminosities per unit stellar mass, and if some of the high redshift galaxies observed by Webb contain population 3 stars, this could contribute to their high luminosities without requiring extremely high total stellar masses. However, population 3 stars are also expected to be rare and short-lived, so their contribution to the integrated light of a galaxy would be significant only if the galaxy is very young and observed soon after the first burst of population 3 star formation, which would require redshifts higher than even Webb can easily probe, or if population 3 stars continue to form in small pockets of metal-free gas even in later systems, which is theoretically possible but uncertain. The transition from population 3 to population 2 star formation and the conditions under which this transition occurs depend on the level of metal enrichment required to change the cooling properties of the gas. Even a very small metallicity, of order 1/10,000th of solar, is sufficient to introduce additional cooling channels via fine structure lines of metals like carbon and oxygen, which allows the gas to cool to lower temperatures and fragment into smaller, lower-mass stars. This transition may happen after only a few supernovae have enriched a region, so the era of pure population 3 star formation may be very brief, and most of the star formation, even at very high redshift, may already involve some metals. Observationally, detecting the transition is difficult, because it requires measuring very low metallicities and distinguishing the spectral signatures of metal-free versus metal-poor stellar populations, which are subtle. The contribution of different types of stars to the ionizing photon budget also depends on the stellar populations. Massive, hot O and B stars emit most of their light in the ultraviolet and produce the majority of ionizing photons, while lower-mass stars contribute little. The number of ionizing photons per unit stellar mass formed depends on the initial mass function, with a top-heavy initial mass function producing more ionizing photons, and on the stellar metallicity, because metal-rich stars have stronger stellar winds that can reduce their effective temperatures and ionizing photon output. The ionizing photon production efficiency, often parameterized as the ratio of ionizing photon production rate to ultraviolet luminosity, is a key quantity for linking galaxy observations to reionization, and measuring it at high redshift requires combining ultraviolet luminosity measurements with estimates or observations of the ionization state of the surrounding gas. The escape of ionizing photons from galaxies into the intergalactic medium, which we mentioned earlier, is facilitated by the presence of channels or holes in the neutral gas distribution through which photons can travel without being absorbed. These channels may be created by feedback, which blows cavities in the gas, or by the geometry of gas accretion, which may leave low column density paths, or by the stochastic distribution of neutral gas clouds. Observations of Lyman continuum leakage, the detection of flux at wavelengths shorter than the Lyman limit at 912 angstroms in the rest frame, which would be absorbed by any neutral hydrogen along the line of sight, provide direct measurements of the escape fraction. But such observations are difficult because the Lyman continuum is observed in the far ultraviolet, or even extreme ultraviolet from the ground, or even from space at low redshift, requiring space-based observations, and the signal is weak and easily contaminated by lower redshift interlopers. At high redshift, the Lyman continuum shifts into the near ultraviolet or optical and becomes accessible, but the intergalactic medium itself is opaque to Lyman continuum photons unless the line of sight happens to be through a rare, highly ionized region, so detecting Lyman continuum escape at high redshift is still challenging. Webb is not optimized for these observations because its wavelength coverage starts in the red optical at best, and Lyman continuum observations require ultraviolet sensitivity, but future missions or coordinated observations with ultraviolet-capable telescopes could provide these measurements. The radiation pressure from stars, particularly from massive stars in compact star-forming regions, can exert a force on dust grains that couples to the gas through collisions, and this radiation pressure can drive winds and contribute to feedback. The effectiveness of radiation pressure feedback depends on the optical depth to infrared radiation, because the radiation pressure force is proportional to the momentum flux of the radiation, which is the luminosity divided by the speed of light, and if the region is optically thick, the photons scatter multiple times before escaping, multiplying the force. In very compact, dusty starbursts, radiation pressure can be dynamically important and can expel gas at velocities comparable to or exceeding the escape velocity, contributing to the regulation of star formation. The comparison between observations and simulations is central to testing models. Simulations of galaxy formation run on supercomputers, evolving the distribution of dark matter and gas from the initial conditions through cosmic time, using the laws of gravity, hydrodynamics, and thermodynamics, and including prescriptions for star formation, feedback, and other astrophysical processes. The simulations produce synthetic galaxies that can be compared statistically to observed galaxies. If the properties of the simulated galaxies, their masses, luminosities, sizes, star formation rates, metallicities, morphologies, match the observations, the models are validated. If there are discrepancies, the models must be adjusted. The rewriting of the map is informed by this comparison. Webb's observations reveal discrepancies, and theorists adjust the simulation parameters or prescriptions to try to match the new observations while still matching other data. And the adjusted simulations make new predictions that can be tested by further observations. Some simulations, called zoom-in simulations, focus on individual halos or regions, simulating them at very high resolution to capture the detailed physics, while cosmological simulations cover large volumes to capture the statistical properties of the galaxy population, but at lower resolution. Both types are valuable, and the results must be consistent across different approaches. Recently, simulations have achieved sufficient resolution and sophistication to begin reproducing the properties of individual observed galaxies, allowing direct one-to-one comparisons, though such comparisons are still limited by the computational cost and by the uncertainties in the input physics. The parameter space of possible models is vast, with choices about the initial mass function, the star formation efficiency, the feedback efficiency, the mass loading factor, the escape fraction, the dust properties, the metal mixing, the AGN accretion and feedback, and many others, and exploring this parameter space systematically to find the models that best fit the full range of observations is a major undertaking. Machine learning and statistical techniques are increasingly being used to navigate this parameter space and to identify the regions that are consistent with observations, and to make predictions that can be tested. The role of magnetic fields in galaxy formation is less well understood than other processes, because magnetic fields are difficult to observe directly, and their effects are complex. Magnetic fields can provide pressure support against gravitational collapse. They can regulate the rate of star formation by stabilizing gas clouds. They can affect the propagation of cosmic rays and the coupling of gas to radiation, and they can influence the structure of outflows and jets. Simulations that include magnetic fields are more computationally expensive and less common, but they are beginning to show that magnetic fields can have significant effects, particularly in the densest, most star-forming regions and in the vicinity of AGN. Observational constraints on magnetic fields in high redshift galaxies are sparse, but they can be obtained through polarimetry or through synchrotron emission, and future observations may provide more information. Cosmic rays, high-energy particles accelerated by supernova shocks and other processes, also contribute to the pressure in the interstellar medium and can influence star formation and outflows. Cosmic rays can provide additional pressure support and can drive winds by streaming out of the galaxy and dragging gas with them through magnetic interactions. Including cosmic rays in simulations is also computationally challenging, but it is increasingly being done, and the results suggest that cosmic rays can have effects comparable to thermal feedback in some regimes. The turbulence in the interstellar medium, driven by supernova explosions, stellar winds, gravitational instabilities, and gas accretion, affects the structure of the gas and the efficiency of star formation. Turbulence creates a complex, clumpy structure with a range of densities and velocities, and star formation occurs in the densest clumps where gravity overcomes turbulent pressure. The level of turbulence, characterized by the velocity dispersion, is observed to be higher in high redshift galaxies than in nearby galaxies, possibly because of higher gas inflow rates and more frequent supernovae, and this higher turbulence may support thicker disks, suppress bar and spiral arm formation, and affect the overall efficiency of star formation. The stability of gas disks against gravitational collapse is quantified by the Tumri parameter, which compares the stabilizing effects of rotation and thermal or turbulent pressure to the destabilizing effect of gravity. When the Tumri parameter is below a critical value, the disk is unstable and fragments, leading to star formation or the formation of clumps. Observations suggest that high redshift disks are often marginally stable or unstable, consistent with the expectation that high gas fractions and high turbulence lead to vigorous star formation and clumpy structures. The energy budget of galaxies, accounting for the energy input from stars and AGN, and the energy radiated away or stored in bulk motions, kinetic energy of outflows, or potential energy of lifted gas, provides a consistency check on models. The total energy released by star formation over the history of a galaxy, which can be estimated from the stellar mass and assumptions about the initial mass function, must be sufficient to explain the observed outflows, the heating of gas, and the expulsion of gas, or else feedback is insufficient, and more gas should remain in stars. Conversely, if feedback were so efficient that it expelled all the gas, no stars would form, so there must be a balance, and understanding this balance is key to understanding why galaxies have the properties they do. The baryon fraction in galaxies, the ratio of the mass in stars and gas to the total mass including dark matter, is observed to be lower than the cosmic baryon fraction, which is the ratio of baryon density to total matter density in the universe, about 16%. This deficit indicates that a significant fraction of baryons that fell into halos has been expelled or prevented from cooling and forming stars, which is the integrated effect of feedback over the history of the galaxy. The baryon fraction varies with halo mass, being lower in low-mass halos, which have shallower potentials and lose baryons more easily, and approaching the cosmic value in the most massive halos, which retain baryons more effectively. The variation of baryon fraction with halo mass is a key prediction of models and is tested by observations of galaxy masses and clustering. The rewriting of the map is not only about the high redshift universe but also about how the high redshift universe connects to the present day, the pathways by which the galaxies we observe at high redshift evolve into the galaxies we see today. Tracing these pathways requires understanding the merger history, the star formation history, the chemical evolution, and the structural evolution of galaxies, and it requires connecting observations at different redshifts into a coherent picture. The galaxies observed by Webb at z equals 10 are the progenitors of present-day galaxies. But identifying which present-day galaxies they evolve into is not straightforward, because individual galaxies cannot be tracked over time, and the connection must be made statistically by comparing the properties of galaxy populations at different epochs and by using simulations to model the evolutionary pathways. The descendants of high redshift galaxies are thought to be a mix of present-day galaxy types, depending on their masses and formation histories. Low-mass high redshift galaxies may be the progenitors of dwarf galaxies, or they may be accreted by larger systems and become part of the stellar halos of massive galaxies. Intermediate mass high redshift galaxies may grow into present-day spiral or elliptical galaxies through continued star formation and mergers. Massive high redshift galaxies, if they exist, may be the progenitors of the most massive elliptical galaxies, or the cores of galaxy clusters, though this is uncertain and depends on how their star formation is quenched and whether they continue to grow in mass. The stellar halos of present-day galaxies, the diffuse extended distributions of stars surrounding the main body of the galaxy, are thought to be built up through the accretion of smaller galaxies, and the properties of stellar halos, their masses, metallicities, and structures provide clues about the merger histories of their host galaxies. Observations of stellar halos are challenging because the stars are spread over large areas and have low surface brightness, but they can be studied in nearby galaxies through deep imaging and in the Milky Way through star counts and kinematics. The connection between stellar halos and the accretion of high redshift dwarfs is an area of active research, and the properties of high redshift galaxies observed by Webb inform models of stellar halo formation. The environment of galaxies, the presence of nearby companions, the density of the region, and the location relative to large-scale structure affects their evolution, and this environmental dependence is observed in the local universe and at intermediate redshifts, with galaxies in dense environments being more likely to be quenched, more likely to be elliptical, and less likely to be forming stars actively. At high redshift, environmental effects are expected to be less pronounced because the universe is more homogeneous, but protoclusters and overdense regions do exist, and studying the galaxies in those environments compared to field galaxies provides insight into the early stages of environmental processing. The cosmic web, the network of filaments and sheets of dark matter and gas that connects galaxy clusters and groups, channels gas flows and affects where and how galaxies form, and the structure of the cosmic web is predicted by simulations and is increasingly being observed through the distribution of galaxies and through the absorption signatures of gas in the spectra of background sources. The relationship between galaxies and the cosmic web at high redshift, and how galaxies trace the underlying dark matter distribution, is being studied through surveys that map the three-dimensional positions of galaxies, and Webb's spectroscopic capabilities contribute to these surveys by providing precise redshifts for faint, high redshift galaxies. The rewriting of the map is ongoing, and the conclusions drawn now are based on the early data from Webb, which represent only a small fraction of the observing time that will be devoted to studying the high redshift universe over the mission's lifetime. As more deep fields are observed, as more spectroscopic follow-up is obtained, as larger area surveys are conducted, and as the data are analyzed with refined methods and models, the map will continue to evolve, and new surprises are likely to emerge. The history of astronomy is full of examples where improved observational capabilities revealed unexpected phenomena: quasars, gamma-ray bursts, dark energy, exoplanets, and it is reasonable to expect that Webb will continue to challenge our understanding in ways we have not yet anticipated. The process of discovery in astronomy involves not just detecting new objects but understanding what they are, how they fit into the larger picture, and what they tell us about the physical processes at work. The high redshift galaxies observed by Webb are being scrutinized from every angle, with theorists proposing interpretations and models, observers designing follow-up observations to test those models, and the community engaging in discussions and debates about the implications. This is the scientific method in action, and the rewriting of the map is the outcome of this process, a collective refinement of our knowledge driven by new data and by the critical evaluation of that data. The philosophical implications of understanding the early universe extend beyond the technical details. Knowing how galaxies formed, when stars began to shine, and how the universe transitioned from a dark, uniform state to the rich, structured cosmos we see today addresses fundamental questions about origins, about the conditions that led to the emergence of complexity, and ultimately about the environment that made life possible, because stars produce the heavy elements essential for planets and biology, and galaxies provide the stable environments where stars and planets can persist. The rewriting of the map is a chapter in the larger story of understanding our cosmic context, and while the work is technical and detailed, the broader significance is profound. The humility required in science, the recognition that our models are provisional and that nature is under no obligation to conform to our expectations, is essential. The surprises from Webb remind us that we are still learning, that the universe is more complex and diverse than we have fully captured in our models, and that there is much more to discover. The rewriting of the map is not a failure of previous work, but a natural and necessary part of the scientific process, and it reflects the power of new observations to reveal aspects of the universe that were previously hidden or poorly understood. The connection between the smallest scales, the formation of individual stars and the initial mass function, and the largest scales, the cosmological model and the initial conditions, illustrates the breadth of the challenge. Galaxy formation is a multi-scale problem, and no single observation or model can capture all aspects. The rewriting of the map involves integrating insights from many different observations, from many different wavelengths and messengers, and from theory, simulations, and empirical studies into a coherent framework that respects the constraints from all sources. The uncertainties we have discussed are not obstacles to progress, but rather the frontiers where progress is made, the places where new observations have the most leverage and where theoretical development is most needed. Quantifying uncertainties accurately and distinguishing between statistical uncertainties, which can be reduced by collecting more data, and systematic uncertainties, which require understanding and mitigating biases in the data or assumptions, is a key part of the work, and it is what allows robust conclusions to be drawn even in the presence of incomplete information. The collaboration between observers and theorists is essential. Observers provide the data and the challenges, the phenomena that need explaining, and theorists provide the frameworks, the models, and the predictions that guide observations and that suggest new tests. The dialogue between the two communities drives progress, and the rewriting of the map is a joint effort, with each side contributing expertise and perspective. The long timescales involved in astronomy missions, from concept to launch to science operations, require sustained commitment and vision. Webb was conceived in the 1990s, began development in the early 2000s, faced numerous technical challenges and delays, and finally launched in late 2021, more than 2 decades after the initial concepts. The scientists who proposed the mission and designed the instruments have in many cases retired or moved to other projects, and a new generation of researchers is now analyzing the data and making the discoveries. This continuity across generations is characteristic of large scientific endeavors, and it underscores the importance of mentorship, training, and the transmission of knowledge and skills. The public interest in astronomy, the fascination with the cosmos and with questions about origins and the nature of the universe, provides societal support for missions like Webb and for the research that follows. The images from Webb, the deep fields showing thousands of distant galaxies, the spectra revealing the compositions and motions of those galaxies, and the stories about what they mean, engage the public imagination and inspire the next generation of scientists and engineers. The rewriting of the map is not just an academic exercise, but part of the broader cultural endeavor of understanding our place in the universe, and communicating the findings to the public is an important responsibility of the scientific community. The data from Webb are being used not only to study the early universe but also to test the tools and methods that will be applied to data from future missions. The analysis pipelines, the statistical techniques, the simulation codes, and the interpretation frameworks developed for Webb will be refined and extended, and they will inform the design of future observatories and surveys. The lessons learned from Webb, both the successes and the challenges, will shape the field for decades to come. The technical documentation, the calibration files, the software tools, and the data products produced by the Webb team are made available to the community, enabling independent verification, reanalysis, and the application of new methods. This open-access approach is standard in astronomy and is essential for the credibility and robustness of the results. It allows for independent cross-checks, for the development of new analysis techniques, and for the combination of data sets from different sources, all of which contribute to the rewriting of the map. The interdisciplinary nature of the work, drawing on physics, astronomy, computer science, statistics, and engineering, reflects the complexity of the problems being addressed. Understanding the early universe requires expertise in many areas, and the teams working on Webb data include specialists in observational techniques, data reduction, spectroscopy, photometry, image processing, theoretical modeling, numerical simulations, statistical inference, and more. The collaboration and communication across these disciplines is key to making progress. The challenge of conveying the findings to both specialist and non-specialist audiences requires different approaches. Technical papers, published in peer-reviewed journals, provide the detailed results and methods for the specialist community, while press releases, popular articles, and public talks communicate the broader significance to a wider audience. Both are important, and the skill of translating complex technical work into accessible narratives is essential for ensuring that the public understands and values the research. The investment in missions like Webb, which cost billions of dollars and involve international partnerships, is justified by the scientific return, the advancement of knowledge, and the technological development that accompanies such projects. The technologies developed for Webb, including infrared detectors, cryocoolers, precision optical systems, and deployment mechanisms, have applications beyond astronomy and contribute to broader technological progress. The economic and societal benefits of space science missions are documented, and while the primary goal is scientific discovery, the secondary benefits are substantial. The inspiration that missions like Webb provide, the sense of wonder and curiosity they evoke, and the demonstration of what humanity can achieve through cooperation and ingenuity have value that extends beyond the specific scientific findings. The images of distant galaxies, The knowledge that we are seeing light from the earliest epochs of the universe, and the understanding that we are uncovering the history of how galaxies and stars formed, resonate deeply and remind us of the scale and beauty of the cosmos. The rewriting of the map is not complete, and it will never be truly complete, because there is always more to learn, deeper observations to make, finer details to resolve, and new questions to ask. Each answer raises new questions, and each discovery opens new avenues of inquiry. The map is a living document, continually updated and refined, and the work continues, driven by curiosity and by the fundamental human desire to understand the universe and our place within it. And the observations by Webb that looked deeper than ever into the early universe are a major step in that ongoing journey, revealing that the universe in its youth was more active, more diverse, and more capable of forming structure than we fully anticipated, and requiring us to adjust our models, to refine our understanding, and to continue the process of mapping the cosmos.